Welcome everyone, and thanks for choosing this video. Today I'll be talking about how Satellite QE does dynamic test infrastructure, or how we rebuilt our test infrastructure from the ground up. My name is Jay Callahan, and I am the automation lead for Satellite QE. So first, let's cover a bit of background. Satellite is a monolithic product. It's comprised mainly of 4 upstream projects and has a number of dependencies based off of those. Our minimum system requirements to run Satellite are 20 gigs of RAM, a 4-core 2 GHz CPU, and a baseline 50 gig disk. Depending on what you're doing with Satellite, those minimum requirements can quickly grow. And because it's so monolithic, the installation time from base rel takes approximately 1 hour. Just running the installer with minimal changes takes around 15 minutes by itself. Additionally, Satellite QE has a lot of tests. We currently have a bit over 5,000 tests that we run per snap. If we were to run all these one by one, it would take about 110 hours, which is roughly 4.5 days to finish. Assuming we get at least 1 snap per Friday, US-based associates could review the results on Wednesday. However, those based in India and Europe would likely see results on Thursday. So the day before the next snap. Obviously not ideal. Now let's talk about the old state of our automation. We traditionally tested on 4 main satellites. That's 1 satellite per testing tier. Initially, each of those was installing Satellite from scratch. So that'd be 1 hour per tier as a baseline before tests even start running. In order to speed up the execution, we would run those tests in parallel on a single satellite target. Now, while that did speed up overall execution, it did occasionally result in race conditions. Well, luckily, near the beginning of 2020, Sadir implemented a new organizational structure for our team, and as part of that, functional teams were created. These are 3 teams that have a dedicated lead and part-time members. Those teams are around our CI, what we call SatLab, which is our infrastructure, and automation. We additionally had 1 functional lead to keep us all in line. Now that we had these people directly focused in these areas, we had the time and resources to do a redesign. And so we did. We set down some requirements for our redesign. Key among these must be usability, meaning it must be as easy for users to get systems as it is for our CI to get systems. And we must be able to easily integrate this into our automation. We needed this to be as stable as possible. These systems needed to just work when we needed them. There are times where we get multiple snaps a week across different versions of Satellite, and these systems needed to be ready for when we are running automation, or when our associates are doing manual testing. Additionally, speed and scale were other key factors, for obvious reasons. Waiting 1 hour for a satellite after you requested one had to go. And we knew we wanted to solve the problem of our test execution time by scaling the number of concurrent satellites that we're testing at the same time. So here's our implementation overview, or our plan of action. We wanted Rev and OSP to be our hypervisors. The initial focus was going to be on Rev. These would be hosting satellites, capsules, and normal hosts, as well as any kind of persistent infrastructure services, like Podman hosts or repository hosts. Ansible Tower was going to be the orchestrator of this. Ansible Tower was going to automate the installation, templatization, and deployment of each of these resources. And finally, we'd use Broker as an interface between the users, automation, CI, and Tower. It didn't exist yet, and we'll get more about that later. So, here's our infrastructure diagram. This is made entirely in Google Slides, and I am not an artist, so forgive me for the way that it looks, but I think it gets the message across. At the very bottom, we have our automation represented on the left by the tests. We have our CI and users. Each of these uses the tool Broker. Broker then will reach out to the corresponding provider, currently Ansible Tower, and in the near future, also container hosts. Ansible Tower would then reach out to the corresponding provider, whether they be Rev or OSP, to deploy specific VMs and pass that information back to Broker. Broker then relay that information back to either the test, the CI, or users, and in the event of the automation, it can also do some additional functionality. But this is the basic flow. Ansible Tower doing most of the work, and Broker standing as a middleman, providing a consistent interface for the consumers of our infrastructure resources. Okay, now let's talk about the requirements we had for Broker. So we know we needed a tool for both users and our automation. This tool needed to have an easy-to-use CLI, an easy-to-use Python library, and a flexible, you can read lazy, configuration. It needed to abstract away most of the details, meaning that you need to know that you are using something, not how you're using something. So you know that you are talking to Ansible Tower, and Ansible Tower is talking to Rev. You don't need to know how it's doing it. You just tell it what you want, and it does it. And it also needed to be extensible. We knew from the beginning that we were going to be branching into using containers within our automation, so we also wrote Broker so that others could easily contribute new providers and extend the CLI. And a bit later, Broker was realized. So, Broker is what we call an infrastructure middleman, meaning that his job is to abstract away implementation details, specifically to provide an easy, consistent interface for users to obtain and manage infrastructure resources. So you should have approximately the same interface whether you're talking to Ansible Tower or a container provider, talking directly to Rev or OpenStack, or any other kind of provider. For example, in the command that you see, the user runs broker checkout, passes in a nick or a nickname saying rel 7, more on this later, and with that, Broker talks to Ansible Tower, gives it exactly what Ansible Tower needs to be able to fulfill this request, and once that's complete, Broker lets you know the host that you got back. It also stores this information locally in what's known as an inventory. Additionally, if we look at the code example, it's effectively a two-line context manager doing exactly the same thing. The only difference is that it's yielding a host object, meaning that the automation can do something with that host object. And then once it's done, it performs a check-in as a part of that. The main design themes around Broker revolve around flexibility, shortcuts, and simplicity. Combining nested configs with arbitrary nicks, or nicknames, users can create their own shortcuts. By limiting the exposed functionality, the interface also remains simple. However, by limiting most argument constraints, we can lessen our direct ties to provider implementation details. This means that a new workflow can be created or an existing one updated without Broker needing to be updated to account for the new workflow arguments. This allows people to contribute directly to SATLab via Ansible Tower and never have to touch Broker in a development role. By maintaining a consistent CLI and library experience, it makes it easier for CLI users to determine the library use. As you can see here, the arguments are effectively the same as you would use on the CLI. As a side note in the code example, since Broker provides a base host class, you can extend this base class for Broker to construct the classes for you. We use this to construct content host, capsule, and satellite classes, each with their own automatic setup and teardown methods. Remember that with Broker's context manager, when you enter the context manager, that's a checkout, and when you exit the context manager, that's a check-in. Now this is where it becomes truly dynamic. We combined PyTest with the XDist plugin, with Broker and SATLab to come up with this. We use a session-level auto-use fixture to determine our satellite target alignment for each XDist worker. There are a few possible modes with this method. Run on one, meaning all XDist workers will run on one satellite, which is like what we had before. Balanced, which attempts to balance the XDist workers on the satellites that are available, as well as on-demand. On-demand behavior will use Broker to check out a new satellite when needed. It can also check that satellite back in once the test is complete. This also means that if a worker dies for some reason, the next one can easily pick up and keep going. One important thing to note here is that users don't actually have to fill out this hostname section of their config on the right. As long as they have a broker inventory, which is locally readable, that can pull in the host names of every satellite that matches their specific criteria. So let's see this in action. Here we see our Jenkins job checking out 10 satellites ahead of the PyTest session running our high tests. However, one of the checkouts failed, so only 9 were checked out. Typically, this would be a problem, but we're using on-demand mode. So the 9 Exodus workers immediately start testing on their satellites, while the 10 sees it doesn't have one, and checks a new one out. It then starts testing as soon as it gets one, joining the rest of the group. In the near future, we'll be skipping the pre-checkout behavior in favor of on-demand only. This means we can start testing even sooner. So how's it going? Well, the new process is working beautifully. Our redesign dream has largely been realized. We've completely replaced our old setups. Associates having quick access to the same systems and tools as CI means that the tests developed locally are much more likely to work in CI. Polling has also been a huge addition. We can now get a satellite in 5% of the time it used to take. And since broker hosts provide SSH2 Python connections for free, we've completely removed Paramiko, further speeding up our tests. For those of you watching on YouTube, thank you for watching, and please add any comments that you have down below, and I'll try to answer them to the best of my ability. And while you're thinking of it, I'd like to thank the people below, namely Mike Shriver, Brian Herring and his SatLab team, Lukash Pramuk and the CI team, as well as the automation team and many more people that contributed to this. Until next time.